I speed up a bit? Hello, everybody is happy. Yeah, is the speed okay? I will continue. Following the speed I was having. Well, I think I will have to speed up a little bit. I was going too slowly before. But if anybody wants me to go a bit more slowly on any more difficult part, then simply tell me. Okay, let's go to the next part. So if we go again, if we have a quick look again to the index, so to speak, to the structure of the codes. So in the next few lectures, I will continue talking about the how neural networks specifically encode for the meaning of words, how you build embeddings. And there are quite some sophisticated ways, but I will talk about the standard ones that almost everybody uses, although now most people is replacing it with simply language models, which I will be talking, I think, next week, yeah. Okay, so let's see, yeah, this is the remaining of the course, not need to update because you just heard about it. And then I will go very quickly through the recap of previous class because it was just now. So, okay, so we go to be able to get the word representation of, numerical representation of words. You get a corpus, you use a vector representation, so points in dimensional space, you use a model, in this case a neural network, and then you go through each central word. Every time you go through each central word, you modify the neural network a little bit in order for it to capture that probability a bit better ever and ever until it kind of saturates. And then you repeat the two previous steps over and over again until you get the best performance. So at some point, the neural network will stop being able to further improve, or it might start even overfitting, but that happens with all algorithms. These were the previous diagrams, so remember, in word2vec you have originally two different approaches, a continuous bag of words and skipgram. The one I have been explaining in more detail was skipgram, but the continuous bag of words is more or less the same, but in reverse. This was the previous diagram that before, so we have one hot representation of the central word. You multiply it by the dense connectivity, the dense connection, which is simply a typical matrix. That's simply selecting the row of this connection matrix that corresponds with the central word. Then you apply the transform of the dense the dense connection, and that ends. You end up in the original 150 dimensional space where every dimension is a word. You apply a softmax to enhance which words, which dimensions are hot dimensions are getting the highest value, and that's it. And then later you compare that to the actual context words and backpropagate the information. These were the previous equations as before. I can explain further if anybody has some question. Yes, and now we are going to talk a little bit more about learning. So learning, okay, it seems quite trivial. You simply apply backpropagation. I will explain exactly what is backpropagation in the next lecture, but for now simply believe me that backpropagation tends to work well, and it drastically simplifies the problem of learning in a neural network. But then in this approach we have a problem, which is the denominator of this equation is extremely large. If you have V is 150,000 dimensions, you have to sum 150,000 times, you have to multiply 150,000 times 3 matrices, so it is computationally crazy. We cannot do it yet, maybe in the future, but we cannot do it. You have to find a workaround. So the way they originally proposed, and it works quite well, is what is called negative sampling. So the idea here is that rather than adding up this product, this exponential across all the words in the vocabulary, why don't we simply apply it in a few words, in enough words for this summation to become more or less proportional to the summation that you will get if you sum every possible word in the vocabulary. And the way you can also do exactly what I said, which is conceptually the steps they follow, is that you select, in every step of the algorithm, you select what is called a true pair. So a true pair is a central word and the real context of that central word. And then for each one of these pairs, you select a few noise pairs. So a few noise pairs is any other, so it is the same word, but with contexts randomly selected from other words. And then what you try to do is to train the neural network for it to maximize the probabilities that the word that the neural network gives you actually belongs to the true pair, while the probability of getting any of the noise words is minimized, is reduced to zero. So what this is able to do is that imagine that you have selected 10 different noise words, and in that reduced example, all the words that appear on the true pair and the other 10 pairs, all the words that appear in those 11 pairs actually have a vocabulary of how much? 30 words. So actually this summation ends up being only 30, because you only have to sum across all the different words that appear on those 11 pairs. So you don't need to sum all the other words, because in your training set for that iteration of the algorithm, all the other multiplications or all the other elements are zero. They simply don't appear in that training set. And then you apply that one time, you apply backpropagation for these numbers to approach to the real context word. And then in the next iteration, you don't use the same noise words, you select another set of noise words. And the thing is that if you do that over and over again, the neural network is still able to learn quite well, but you actually don't need to do a summation across all the possible existing words. And then again, the result that you get, even if you simplify the problem in that way, is the result that we were talking about. All the words that have similar meaning, they appear close to each other. The ones that have different meaning appear quite far away from each other. Then later you also see this example. I think it is handcrafted. You never get something so beautiful so far with any algorithm. But what you see is that different dimensions, different directions in the embedding space represent for different changes in meaning. This is the example that everybody uses. Dogs and cats, they also love them in the field, so they also, this other dimension represents change to plural. This other dimension represents the relationship between capitals and cities, and the same with many other both grammatical and semantic relationships. And also something important to have into account is that this tends to work very well. You tend to see this stuff with the very frequent words that appear a lot in your training set. But with the more weird words, like a very exotic breed of dog, then you might not find these relationships being so nice, simply because there was less training data about that word. Okay, so this was the word-to-vec problem. But then someone might ask, so if we are extracting all this information simply by the property that words that have a similar meaning share the context, why don't we do it in another much more direct way rather than going through that detour of using neural networks? And that's what, for instance, another algorithm called Co-occurrence matrices try to do. Yeah. So what a co-occurrence matrix does is simply counting what are the words that tend to appear in context, and then you put that into a very big matrix, and that matrix is capturing all that information about the relationship between central words and the context. So maybe the meaning, all the good features that we are picking up with our neural network, with our word-to-vec, maybe they are encoded in that count matrix. And let's see how it works. So you have a corpus, like for instance, this one is the same handcrafted example from before. And then what you do is you build a matrix where you have as many rows as words in the vocabulary, 150,000. You have as many columns as words in the vocabulary, again, 150,000. And every time that you go through word to word or through sentence to sentence in your vocabulary, and for every central word, you look at the context and you count. You add a +1 for every combination of words. So here, in the row of your count matrix that corresponds to dog, and the column that corresponds to fur, you add a +1. And you do that over and over again in a very big corpus. And then you end up with a matrix like this one. And then you see here that you end up with the same property that we were trying to capture with the neural network. You see that words that are very similar or that have more or less the same meaning or related meaning, they end up with a vector, with vectors that are quite similar to each other. Maybe not similar in this example, I have idealized it, maybe not similar in the exact count, because dog is much more frequent than Labrador, so dog will have much higher values. But when you multiply one by the other, which is what the softmax function was doing in the neural network, they project to each other quite strongly, because they are pointing very much in the same direction. Simply one of them, so in n-dimensional space, you are going to have something like this. The word for Labrador might be like this, where this is simply the 0 vector. And the word for dog is going to be way, way larger, but it is going to point in the same direction. So when you do the scalar product, then the value of the scalar product is similar to the modulus of the smallest of them. And that's what you are trying to maximize. And words that are very dissimilar with each other, like cat and dog, when you project them with each other, when you multiply each guy with each guy, each number with each number, and you sum everything up, you are going to get a much smaller value. So they are mostly perpendicular to each other. But then, okay, so here it seems that in the count matrix, we are capturing quite well, with a much simpler method, all the nice properties of the embeddings, but we have some problems. Some of the typical problems that were common before using neural networks in most methods. The first one is that in the neural network approach of embeddings, the matrix where we are encoding all the meaning of words is a matrix with, okay, many rows, as many rows as you have in the vocabulary, but only d columns. So it is much smaller than the matrix that you get with the count, with these co-occurrence matrices, because in the co-occurrence matrix, it is 150,000 dimensions by 150,000 dimensions. So you again end up with the problem of having a crazy matrix. So that requires a lot of storage itself. Then if you want to increase a bit your vocabulary, because you can say, oh, well, then simplify the problem. Let's focus on the most typical words, or the 1,000 words that are most important for your application, your industrial application. But the problem is that as soon as we want to increase a bit the size of the vocabulary, the matrix grows as with the complexity of b squared. Then that, of course, requires a lot of computation. Every time that you want to see the distance between two words, you have to multiply 150,000 numbers rather than only 200 numbers. And the more serious problems is that rare words will end up with very low counts in the matrix and also very noisy counts. Depending on your corpus, the direction of the vector of infrequent words is going to change dramatically. So that's one of the typical sparsity problems. In the words that are not very common, or not even in the words that are very common, you are going to have a lot of zeros in the matrix. And that generates quite some problems. But then there were ways of ameliorating this problem, which effectively end up producing a dense representation of the space. So through another method, they are ending again with embeddings. Also, I think they don't call them like that because it wasn't with a neural network. But what you do is, okay, but why don't we apply some of those many methods that there are around that preserve the information encoded on the distance between vectors in the space. So before, when I was showing all those nice diagrams where we represent in 2 dimensions what happens in the 200-dimensional space of the embeddings, and where we saw in 2D how similar words are close to each other, those are that type of approaches. They are called, one is the most famous PCA, principal component analysis, other one is independent components analysis, other one is, what was it? Some self-organizing maps. That's another one that is very elegant. So there are plenty. So why don't we apply one of those? So yeah, let's apply single value decomposition. So single value decomposition, which they chose that one for another property that it has that I will explain later. Singular value decomposition, what it does is to get a big matrix and decompose in a multiplication of 3 other matrices with specific properties. In this case, we will get C. So in case this yellow is too yellow for people in the back, this is C with dimensions VV. And we decompose it in 3 other matrices, also of dimension VV, so they are huge matrices, multiplied by each other. But they are not any matrices. They are matrices with certain properties. So the matrices U and V, they are one type of matrix. I don't remember just now the name of this type of matrices, that its transpose is the inverse of itself, which is quite beneficial, and it makes something, it has a geometrical property that I will explain now. And V the same, its transpose is its own inverse. Usually the inverse is a crazy matrix that you can only theoretically classify when the matrix is square and blah, blah, blah. Otherwise you need an approximation algorithm. But here, the inverse or pseudo-inverse is simply the transpose. And then epsilon, is that epsilon? Well, that kind of E, the same symbol than summatoria, is a, how do you call this matrix? Pseudo-linear, or I don't remember, but the thing is that it is a matrix like a identity matrix, but it is cut on some point. So you have only values in the diagonal and everything else is 0. And then what these properties M geometrically is that what you are doing is approximating M by first a rotation. So imagine that these are 2 vectors. These 2 arrows, yellow and red. They are 2 vectors representing the counts of 2 different words, yellow word, red word. So you first rotate it when you multiply by V, then later compress each dimension in a different scale. So the way you compress each dimension is dictated by the values of this diagonal part. And then you rotate it again for the vectors to be close to the previous ones. And the good property that this very fancy decomposition has is that when you approximate any matrix, when you approximate M here by that way, and then you cut from epsilon, you cut the lower value. So this is like in the eigenvalue problem for those that were studying digital control or some other dynamical systems in the degree. So these orange values, the first values in the first rows and first columns, they are the highest, and the other ones tend to be lower and lower. So when you start cutting this matrix with starting by dropping the lower columns, those are the ones that are dropping the least information, and the same intuition happens in principal component analysis and the other ways. But the good property that this method has is that when you do that and reconstruct M after cutting the epsilon matrix that you got, you get an approximation of M that approximates the original vectors represented in the rows of M in the mean square error sense. So when you calculate the mean square error between each vector, imagine that the original M is, original M, and the new M is compressed M. So when you calculate the difference between the rows of the old M subtract the corresponding row of the compressed M, and then sum everything up and multiply by, go to the power of 2 and sum everything up. Yeah, the summation is later, I think. Then you get the lowest possible value that you can get with any linear transformation. With nonlinear transformation, like in self-organizing map, you could do better, but with linear transformation, that's the best you can do to minimize the mean square error. And that's why the people working with co-occurrence matrices chose to go for that way. And then when you do the same trick that we were applying with the neural network embeddings, you see more or less the same type of properties. So you see that words that are similar to each other, like, or have some correlated, similar, or associated meaning with each other, they tend to end up close to each other, like bride and priest, teacher and doctor, and so on. And the other ones end up very far away. So you end up in this reduced space that you obtain with singular value decomposition. You end up with something similar to the embeddings. But then there are, when you compare with the neural network, it is still not clearly better. The co-occurrence matrices are not clearly better. The benefits they have is that they train faster, they make efficient use of statistics, so statisticians get very happy. Maybe other more applied people don't care. And then it seems to be quite good to capture word similarity, but the problem is that it ends up giving too much importance to the very high frequency words. So I think the problem that happens is that the words with very low frequency end up having everything 0 or something, but in skipgram and in neural network embeddings, you also have some problems in the infrequent words, but they are not so serious. The problem then that people mention in neural network approaches, like the skipgram, is that they are not so fast, but they are okay thanks to GPUs. An efficient use of statistics, again, I guess statisticians don't like that. But then it tends to have better performance on when you plug it on another task. I will describe later what I mean by plugging another task when I talk about evaluating how good an embedding representation is. And then they can capture things that are more complex than simply word similarity. So they can capture meaning in the directions of the embedded space and so on. Okay, so now, but then the idea arises, or something that you will think could be useful, you could think about it. Give me a second. Okay, nobody will call me. Which is, why don't we try to combine both methods? Perhaps there is a way in which we can combine these two methods in which we get the benefits of both, which is a quite good approach. So then one of the people that was trying to do that were the ones that invented Glove, which is an alternative method of creating word representations that are, or embeddings that was used a lot in natural language processing. They are still used a lot because they are quicker and simpler to use, but now in more complex applications, most people are rather using language models, which I will describe next week or the next one. So the approach is, or the first people that was attempting to merge both methods, they went through a series of, if you read the paper, which is not the most readable paper ever, but if you read the paper, they go through 3 quite heuristic steps. So they describe the steps with some equations and mathematically, but at the end of the day, it was simply rather heuristic choices. So the first heuristic choice, it means that when you look at the data very, very hard, then your intuition tells you more or less what to do. And maybe you have some more clear idea of why that method might work, but you cannot put it in equations very clearly. So the first step, the first thing that they saw is that to solve the sparsity problem, the problem that arises in the very infrequent words, or the problem that arises in between very frequent words and very infrequent words, which, if you remember, very frequent words in the count matrix, co-occurrence matrix ends up having very high numbers, and infrequent words ends up having numbers close to zero and very, very noisy. So what they were proposing is, rather than capturing the meaning of word with the absolute number of counts, why don't we, or what seems to be more stable, more consistent, is the ratio on the word count when we fix a given central count, central word. So if we, for instance, select a central word, the word dog, and then we want to see what is how associated in meaning the words bark and the words park are, then rather than counting all the times that those park and bark appear in the contents of dog, what you do is to focus on the ratio between the number of times that bark appear in the context with the ratio of the number of times that park appears in the context. So that was the first logical step that they do. Then the second step they do is that they think that in the expression that encodes or that builds from that correlation or from that ratio between words, the relationship that builds the embeddings, or the relationship that builds the distance between words should be linear, because they say it will be easier, it will be faster to compute. I think that that was their main argument. So then that reduces dramatically all the possible equations that you can build to represent the distance between words. The next step in their argument was, let me remember, that the distances should be symmetric. So the distance from dog to bark should be, when dog is the central word, should be the same as the distance from bark to dog when bark is the central word. And if you apply those three steps, you end up with, or if you introduce those three restrictions, you end up with finally a manageable equation that you want to approximate. So what they say is that the embedding representation of a word, which is W, for the distance between words to be linear and to be symmetric, they aim to portray in some way the relationship, the ratio between counts of words, it should comply with this property. So the product of two different words, so if you have a word I, WI, then if you multiply by all the embedding dimensions of the other word and you add up two different constants, that's the only or the most complex linear relationship that you can create. And then they say that it also should approximate the logarithm of the count between those two words. So again, you multiply the two different words, which is the distance they want. You also add two different constant values, and that should approximate the logarithm. And for that property for your vector representations to approach this property as close as possible, then what you have to do is you make an error function j equal to the difference of those, because this part of that equation should be as close as possible to this logarithm of x. X here is c. It is simply because I should have used c. I'm using c there. So these two values should be as close as possible. Here I am using simply a bit of the funny nomenclature that I was talking about before. This is a column vector, this is a row vector. You can rotate them any way you want. You add two other values that we are going to calculate. I mean, they are free parameters that also are determined when you try to minimize this error function, and then that has to approximate as much as possible the logarithm of your count, the count of how often these two words appear in the same context. And then later, a totally heuristic step that I think they don't even try to argue it with equations, is that you also multiply that by a function that looks like this. It is a kind of a step function, which what it prevents is it further prevents the very frequent words from dominating the whole equation. And it also prevents the very infrequent words from having a very strong impact on how the W's that you are, on the value of the W's that you are going to obtain, are going to end up with. So that's the three different heuristic steps that they were using in the papers to end up with this equation. And then the advantage they get with this approach is that it seems to be faster to train, and because it is faster to train, you can scale it to very large corpora. So you can train, in rather than 10,000 Wikipedia articles, you can train in the 2 million Wikipedia articles that there are out there. And it seems to work quite well, they say, or well, yeah, when you evaluate them, they seem to work better when the corpus is smaller. Okay, so now we have talked about three different methods, and there are others, but then the question remains, so how do we evaluate how good they are? Because otherwise, we will be talking like in philosophy, proposing a lot of stuff, but then not really being able to check that much. So there are two different methods, the intrinsic ones and the extrinsic. And it is simply a very easy differentiation. So in the extrinsic ones, you try to measure certain geometrical properties of your embeddings, because your intuition tells you that for the neural network or other methods to be able to use them well, there are a number of properties that they should comply, which I will, or they should approximate, which I will talk about later. And then later there is another approach, which is more difficult to compute, because what you do is simply to use the embedding in a real full task. But imagine that you have your embeddings depend how your embeddings end up being depend on 5 different parameters. So for instance, in the example of globe, you have to decide what this X max is going to do, and you also have to decide whether here you put a logarithm or something different, or whether you do here a square or whatever. So there are many options in your embedding that you can play with to get the best possible algorithm. But then, if you are using a full another task like a translation task that takes like 1 month to calculate, how are you going to test all the many different possible combinations of how to do that embedding? So that's why many people in the end go to the intrinsic method, because you can compute it much faster. Okay, and what is an intrinsic method about? So the intrinsic method, as I said before, you get some of the properties that you think should be good, should happen in a good quality embedding, and you test how good they are doing, how close your embedding is coming to it. So one of them is the word vector analogies. So if for any word, a good embedding should have this type of transitional relationship. If you have a vector A is to B, then there should be a way of translating that relationship to another vector C, and be able to give you the vector representation should be able to give you which word X should be equivalent to C as B is to A. And the typical example, as I said before, is man is to woman as king is to what? So king, it will be to queen. The way this works, or the way you evaluate how well your embeddings are doing this, is again with the R-max approach. So you get your original A, B vectors, you subtract one to each other, so computationally you have here A, B, C. The difference of the two vectors is going to be this other vector, and then you move that vector to the other vector C, and which is all this operation, WB minus WA plus WC, that's the vector that you are going to obtain. And then that vector should end up as close as possible, or at least as close as possible in the dot product sense, to the vector that in this relationship should correspond to C, or should correspond to king, which is queen. So if your vector representation, what this is arguing is that if your vector, your embedding representation is good, queen, rather than being here in some crazy place, queen should be somewhere close to the point of this other vector. And then you measure that not only with queen, but with many, many words, with many, many pairs that you have pre-compiled, and see in average how well your embedding is doing. And then, yeah, here you see again this example. Perhaps I shouldn't have gone to it again, but you see king, queen. You see the vector that will correspond to WB minus WA. So if you move this blue vector to other ones, because this is the blue vector that should correspond with the translation, the transformation to female. If you move it to any other vector, to any other word, you should end up with something that in the dot product sense at least ends up being quite close to the female equivalent. And here you see in this embedding, in this example of embedding, for frequent words it tends to work quite well. All of them point in the same direction. And here we have another one for the transforming a word by the comparator and transforming a word to the what was it? Well, to the highest. I don't remember in my English grammar schools when I was a kid what was the name, but yeah, you got the meaning. Yeah, and then the good thing, another problem with the intrinsic methods is that you again need hand-annotated data sets that have a lot of combinations of words that you can use to text those relationships. But there are around. There are some that, at least for the frequent words, a bit like sync sets. Indeed, you could use sync set as well to test something similar to this. So here I have a few websites that have compiled some of those relationships. For instance, in one of them, you have these 4 words that tell you, give you many capitals and each corresponding country, and they do it with groups of 4. But then you could use that to run this calculation with A, B, C, and D being each one of those words in each one of the rows. And then there are other data sets that do something also quite interesting. Also, when I was looking at it for the frequent words, it didn't work too well. But what it does is they have asked many people, perhaps not that many, but they have asked a number of people for every 2 words to give in a number representation how similar they or how closely related they think those 2 words are. And then people simply give values. For instance, when people were asked how close or how related cup and coffee are, people would say, 6. But how close or how related moon and string are? They are very different words, so 0.5. And you have that which is capturing the opinion of the people at that time for many different frequent words again. And then how do the different methods do in the intrinsic evaluations? Well, often when you look at the papers, these intrinsic methods end up scoring quite better in GLOVE. So here, again, this is what I was talking of the parameters. No, this is not the parameters. This is the time that it took to train the model, which itself is kind of a free parameter. So the more that you train a model, if you have a lot of data, the better that it is going to approximate your loss function. And when you compare skipgram to GLOVE, it doesn't matter how much time you keep training the model, the 2 different models, GLOVE end up scoring better in this type of intrinsic methods. And they have here, I think these were two different tasks, I believe. Yeah, I think they were 2 different tasks, or perhaps they are comparing the skipgram method with the CVO method. And then also you can evaluate, you can use, so the example I was giving before of moving the vector that represents female, moving it from one word embedding to another one, you can do it not only, you can do it for different types of relationships. You can do it for vector differences that encode for semantic information and vectors that represent more syntactic information, or simply take vectors for everything. And then if you take GLOVE or skipgram, and you train each one, any of those algorithms or any other embedding algorithm with different data sets, then you see how well they are able to do in the different properties. So what you see here is that the syntactic, the score for how well the geometry of the embedding space is representing syntactic information, it always increases as you get more and more words. But the semantic one, it doesn't increase that much, but anyway, and the same that you are seeing here, how the intrinsic results change with the number, the size of the training, you can do it with other properties of your embedding algorithm. And then other thing that that is very important to do, and that you could also do it with the intrinsic method, also this example is for the extrinsic ones, is that you can compare, if you propose a new method, you can compare the same evaluation with the traditional ones to see if yours is better. But here in this table, what they are doing is comparing different methods of doing embeddings on real tasks. And you can choose any of the typical tasks of NLP. So you can see how good a neural network that you are using for name entity recognition, how well it works depending on the embeddings that you use in the first layer, the same with parts of speech, sentiment analysis, with any one of them. This is an example of a paper, that paper over there, where they use many different algorithms. You see that CBOW and GLOBE are not the only ones, there are many other ones. And they saw how in the test set and in other type of tasks, how well they were working compared to the others. So yeah, that was everything for now. We have finished a bit early. I could have put more information. Well, anyway, I will extend a bit more the other lectures. I was trying to cut them down, thinking that it was going to be too much material. But okay, we have given now the word representations part in these two lectures. In the next ones, we are going to talk about a very typical application, which is name entity recognition. And yeah, later on, we are going to start talking about language models that are much more used nowadays, and machine translation. And then at the end, there are some papers that you could have a look at with information related to this lecture. Also, you should have a look at podcasts and even other courses in YouTube and so on, because that extra source of information has turned out to be extremely useful. So yeah, that's everything. If anybody has some recommendation or would like to say, oh, I think you should go faster and give more material, or other ones, I think you should go more slowly and give less material, then drop me an email. Yeah?
Just a quick question.
Yes.
So is GLOBE now like the state-of-the-art model, or are there more recent approaches to embedding?
There are more recent approaches, but usually when people are using embeddings, usually they apply simply word-vec or GLOBE, any of them. And something strange is that when I have been using word2vec and GLOBE, actually it was word2vec working better, but for some reason in these papers they get better scores in GLOBE. I don't know why. However, now most people is using language models. It is a development of the last couple of years.